right. All right. What's the Taylor series? For a given function, Taylor series is a series defined using the derivatives of the function at a particular point. Okay. So here let's have a quick review. Okay. So for a function f, okay, defined nearby point A, okay, the Taylor series, okay, the Taylor series of f at point A is defined by this formula. Okay, so now you get a series. So the question is when this series is convergent. Okay, for what is the rate of convergence? Does it convergent to the function? So that's two questions was answered by Taylor. Right, question one. What is the radius of convergence? Right. Second. Okay. Does it convergent to the f of x on the interval the right between 4? Okay. So that's two questions here. And then Taylor answers these two questions. That's why we have a Taylor's result, and the Taylor shows us how to we can find a rate of convergence as long as we can get a coefficient. The question is how does it converge into the function? Sometimes yes, sometimes not. Okay, there are some functions it is differentiable as many times as you want, and you get a Taylor series, but Taylor series does not converge into the function on the on its interval. Okay, on the interval convergence. So so the questions. This is this two questions. Taylor already answered your questions. Okay, we can find. Okay, so that's a Taylor's result. Taylor's result is for some d less than r. Okay, if the nth order of the derivative less than m and d depends on d, right? So this is the x minus a less for d, and then the error between them. Okay, k, a, and k bacteria x minus a, and this is less than equal to n plus 1 factorial, m and d, and x minus a to n plus 1. Okay, so that holds for x less than equal to d. Okay, so then clearly if the term on the right hand side converging to 0, so further if the limit approaches if this one actually approaches 0, and we can replace it by d, okay, because x minus x is arbitrary, so the largest possible value for that is d, and this is the d. When this is 0, then at least this function is going to be equal to the series for x minus l less equal d. Now, if these are arbitrary numbers smaller than r, then it holds on the whole interval. That's the idea, right? That's a characteristic work. Now, we have some examples. We already did it. We checked sine, cosine, explanation function and 1/1 minus x. And okay. Now the question is how to find the Taylor series. For a given function. Okay. Then whether I use the definition, but we know that when we solve problems, it's not necessary to use a definition. Okay, method one, which is good, but not. Yeah, method one, use a definition. What is definition? Definition is you have to find the derivative of all the, find the derivative of the function. Okay, that's it. Second, if the function is a special, okay, then you probably can use the already known result to do that. Okay, and so use the power series representation. Okay, so use a series power representation for the function at A. Why? Because we have this very important factor. Okay, the important factor is if this one is the power series representation. Okay, for the f at A. Okay, and was a radius convergence, positive radius convergence. Which can be infinite, but let's say assume I is 0, positive. Then, okay, then it is the Taylor series. Okay, i.e. the Cn is empty. Okay, if we can do that. So you find the Taylor series. Not only that, right? You not only find the Taylor series, you also find the power series for that particular function. Okay. Yeah, given a function, if you know how to find the power series, you actually do more than what we ask. Okay, that given a function, we either ask you to find the Taylor series or find the power series representation. If you want to find the power series representation, you still can go through the Taylor series first. Then you prove the Taylor series convergent to the function. Then this is the power series representation. Or you can use the already known result, you modify it, and you get power series representation. That's great. Okay, right? And but you can also, if I just ask you to find the Taylor series for the function, you don't need to prove its convergency. You don't need to, don't need to show that it's convergent to the function. Then there's two options. One is just use definition, find all the derivatives, right? And evaluate at A. Another option is you do more than what I asked to find the power series representation. Okay, then you solve the problem. All right, so the picture is here. Here's the function. First of all, you get a Taylor series. All right, that's the differentiable. Okay, then if you can do further, you get a power series representation. Okay, then you get a power series representation. But sometimes you can get a power series representation directly at A, right? Directly using known result. Okay? So if you're doing that, then you also get, once you get a power series representation, you also get a Taylor series. So the question is, what I'm going to ask you, okay? If I ask you to find Taylor series representation, you have two ways to go. One is to use the definition, or you can go around, okay, using known result, okay, such as like the 1 minus 1 of x is going to be sigma, right, x to the n, okay, or some other result like e to the x, and so on, right? And this is x is an arbitrary, okay, or sine cosine, right, and the cosine, okay. So those are the those are the already we did this, right? And using those results, you are able to I think this is going to be n equals m equals 2m plus 2 factorial and negative n x to the 2m plus 1 factorial. So when m equals 1, you get an x, yeah, it's ultimate. Okay. And the second one is the even number. X to the 2m, and here I think it's m equals 0. Yeah, first term is the is a 1. Yeah. Okay. All right. So those are the known results. You can use that. So you can go to find Taylor series. Yeah, you have two ways to go. Find the power series. You also have two ways to go. You can go through Taylor series. That's why how did you get it? If you want to find the power series representation for the function, right? If you don't have any known results you can use, then you have to go through the Taylor series first. Then you check the convergence. Then if it's also using the Taylor result, estimate, then you prove it's convergent to the function. Okay, that's why how do we get e to the x and sine x, cosine x? Okay, yeah, that's why how do we get to the power series? So this is a picture I wish you to memorize. Okay, and you decide which way to go. Depends on what kind of questions you ask. Right? They are in either way, either of the question you have two ways to go. Two possible ways to go. All right. Okay. So here's a question. Right. Find the Taylor series for the function f of x equals n of x at x equals 2 at a equals 2. Okay. That's it. So that is a question, and then you have two options. Okay. Right. So look at the picture, right? You want to find Taylor series. Okay, the definition there. So method one, use the definition. Right? Use the definition of Taylor series. And you will see it's not as simple. It's super complicated. X is x negative 1. So the first derivative, negative 1, x to the negative 2, right? And the second derivative, you have to figure out the pattern. Okay, and so on. I think I already figured out f n x, negative 1, negative 2, all the way to negative n, and x to the n, right? All right, now, how can I represent that? There's n terms here, so negative 1 to the nth power. So n factorial, x to the negative n plus 1. Okay. So f of 2 and that will be 2 to the negative 1. Okay, so that is going to be negative 1 to the n, 2 to the n plus 1. And this is the coefficient. Great. And the Taylor series is going to be okay. And after you plug them into the formula, now this particular example is okay. It's not too bad, right? Okay, it's not too bad. You have this. But what we don't know is whether this is convergent. What is the rate of convergence? Is it convergent to the function on which interval? Then you have to do more than, right? If you want to understand more about this series. So, but actually this is by definition, this is a Taylor series. And you can find out now. You cannot just give me the first few terms. That's incomplete. You have to give me this general formula. Okay? Otherwise you do not get the 4 credits. If you just only compute the 3 derivatives and evaluate and give me the first 3 terms, that's just only first 3 terms. You have infinite many terms you haven't given me. How can I give you 4 credits? Okay? Then you say, oh, I have trouble to figure out general formula. Well, that's not the best way to solve the problem, actually. Okay? So how can I use a known result to solve the problem? Okay. The new result, use this result. Okay. Okay. This result says that this power series on the right hand side, okay, is convergent to 1 over minus x for x absolute value of x less than 1. Okay. Okay. So 1 over x is going to be 1 over 2 plus x minus 2 because we want to get x minus 2. Right? So I take the 2 out. What I'm trying to do is I'm trying to express it in this form. U is going to be negative x minus 2 over 2. Okay. Then, when x close to, u close to 0. Okay. U close to 0 when x close to, right? So that's great. Okay. So by the above result, it can be u to the n. That holds when absolute u is less than 1. Okay, then I'll replace u by negative 2 by x minus power and over 2 less than 1. Okay, so I rewrite it again. It's going to be negative 1 to the nth power. I have a 2 to the nth power, then there's another 2 in front. That's 2 to the n plus 1, x minus power. Now this holds when x minus less than 2. So you see, we get this identity. So this is a Taylor series. Okay, this is the Taylor series. Okay, it must be the Taylor series. Okay, this power series, okay, is equal to 1 of x when x absolute x minus 2 is less than 2. So we get more than what we need. We get Taylor series. We also show that the Taylor series is convergent when x absolute x minus 2 is less than 2, and convergent to the function 1 of x. You see, so it's better. Okay. If the function is so special, now not every function you can do that. Not for every function you can do that. Okay. Sometimes you have to use a Taylor series. Okay, you have no choice. Just like e to the x, nobody told you. Nobody have told you the formula, right? for the power series representation of e to the x, then you have to find it by yourself. You have to prove the convergence. Okay. All right. So here's another question. Find the Taylor series for the function natural log at a equals a equals 2. Try this. Either method you can use. Okay, natural log of x is very nice. It's defined. Yeah, note that, right? Natural x is defined on the interval from 0 to infinity. So 2 is there. If you look at the picture, this is a picture. Okay, here's the 1, axis, here's axis, here's 2. So I expect we're going to find the power series, we're going to find the Taylor series and the convergent to the natural of x over the interval here, okay? Over that interval. Okay. So find the Taylor series, please. Do that. I'll give you a minute to think about it. Okay. What I suggest you to do is to use this formula. Natural log of 1 plus x equals n equals 1 to the infinity. That's hold for x less than 1. Okay. So using this, I hope you can solve the problem. Okay. Let me show you how to do it if you haven't got it. So natural log of x, right? You have to express x in the form x minus 2 plus 2, right? You do need it to get it, yeah. Okay, so natural of x is natural log of 2 plus x minus 2. So I take 2 out. Okay, then I get natural of 2, this constant, don't worry about that. Okay, so now this part we call the u. Okay, just natural log of 1 plus u. U close to 0 and x close to 2. It's good. So I get, what is my formula, right? Here's a formula, right? So what I get here is n equals 1, -1 to the n minus 1. Here's n, and u to the nth power, absolute u should be less than 1. Okay? So now you replace natural to the first term. Okay? So this is n, and here's 2 to the x minus 2 to the nth power. And this should be less than 2, right? Yeah, absolute x minus 2 over 2 less than 1, that's equivalent to that. So the radius convergence is 2 here, right? And then, so the interval you're going to get is this interval in yellow color. Okay, so I already predict that at the very beginning. I'm going to rewrite it in the form 2 to the nth power n. So those are the coefficients. Now, it's not easy to, if I give you the if I give a power series representation like this, it's hard to figure out what kind of elementary function it represents. Okay, because in many cases, you don't have an elementary function, represent that power series. Okay, but in this particular, we know where it's from. So now this is going to be the natural log x. Okay, but if I do not tell you where it's from, I just give you this power series. Can you recognize what is that series? Okay, I think it's pretty hard to figure it out. Yeah, it's pretty hard to figure it out. Okay, it's not sometimes yes, sometimes no. Okay. But you have to use the derivatives to find it. All right, here's another question. Okay, find the Taylor series for the function f of x equals e to the negative x at a equals 0. Now, a equals 0, that means sometimes it's also called the Macaroni series, okay? Okay. Taylor series at 0 is also called Macaroni. We try to give some credits to Macaroni. Macaroni probably at the same time. He also discussed Taylor's power series for the functions, and he proved some result similar to Taylor, but it's very special just to focus on the origin, a equals 0. During early days, the communication was not good. So people don't know, living in two different countries, people don't know each other. The result until they're published, and several years later, people see it. People saw it, yeah. Okay, but these days, yeah, communication is very fast, but just too much information there. Still, people don't know, yeah, each other, right? Just too much information there. If you search on internet, right, you type something and get thousands of pages shows up. Okay, everybody is creative, okay? Even you don't have education, people use TikTok, right? Post lots of funny videos there. Okay. All right, so now let's find the Taylor series for this function. I said that you still have 2 ways to go. Okay, but I try to avoid using the definition to find the Taylor series. Okay. Now, if I ask you to find the power series representation for the function, if you use the Taylor series, even that's really not a good idea. If you see the function is very familiar, it's the exponential function. Okay, because you have to prove the convergence. You find the radius convergence, you have to prove it's convergent to the function, right? Okay. All right, so if you just want the power series, I think either way is good. All right. If you just want to find the Taylor series, either use the definition to find it or use a known result. Okay. Use the definition. Let's find the derivative. That's -2 e to the -2x, right? And second derivative and the square e to the -2. So you can quickly get the pattern. Okay, you quickly get the pattern. You can quickly get the pattern. Okay, so you got 0 here. It's -2 to the nth power, right? Then the Taylor series is going to be n factorial. I just said that this is also called the Maclaurin series. Okay, so that's it. It's not that complicated, right? Second method, use the already known result, because we know that e to the x is x to the nth power n factorial. Okay. E to the x. Right. Right. And this holds for any x. So now you replace x by 2 -2x. Nth power. And -2 to the nth power, x to the n. And that's it. All right, so that's the answer. Okay, and since x can be arbitrary, so -2x can be arbitrary. So no restriction. So this holds for x less than infinity. You put a question, okay? You put the condition on x. So that's it. Okay, either way, simple. Okay, but if I want to find the power series representation for the e to the -2x, this is the best way. You use an already known result. If you use a Taylor series, then you have to prove, you have to get an estimate, you have to prove it's converging to the e to the -2x. Okay, and you don't have time to go to the last step. Because time is very limited on the final exam. So here's the next question. And I think this is problem number 22. Okay. No, we did this already. Similar one. I'm not going to do that. All right. So find the power series representation for the function f of x. Now this function is sine x over x, and that's going to be 1. So here's the if x is not going to be 0 if x equals 0. Okay. Now I haven't even tried to show that this function is differentiable as many times. You see, you cannot, even I can change it, like find the Taylor series for this. You have to prove that, you have to find the derivatives for this function, right? And there's no way you can use the Taylor series to get the power series representation. because it's not, you have to give me lots of arguments to show this function is differentiable at its origin. Okay, at a equals 0, right? So the best way to do is to use a known result. Okay, we know that sine x is going to be x to the 2n plus 1. It's 2n plus 1 factorial. Okay. And the first term is x, actually. It's going to be when n equals, it's x. Okay. The second term is when n equals to 1, that's a 3 factorial, x cubed. The fourth term is x to the 5th, I think 5 factorial, and keep it going, right? And this holds for any x less than infinity. All right, so this is sine x. I think clearly, if x is not going to be 0, right? Sine x over x, you can divide every term by x, so you get 2n plus 1, so you get an even function. So this is a series, right? And when x equals 0, and this still holds, okay? So when x equals 0, this still holds, and the 1, when x equals 0, 1 is going to be 0 to the 2n's, right? This still holds. Okay, so therefore, you conclude that f of x equals okay, and this holds for an arbitrary x. Great. So we get power series representation. Now, if I ask you to find the Taylor series or Maclaurin series at its origin, and you get it. This is a Maclaurin series. Okay, because that's this function equal to the power series representation, power series, and that's for any x, right? Then you not only show that this function is actually differentiable as many times as well, and this function, the Taylor series, is just equal to this power series. Here's a question. Now we're trying to solve the inverse problem. All right, we're trying to solve the inverse problem. Oh, here's a stupid question. Okay, it's 1 plus, okay, 2x cubed plus 4x to the 5th. Okay, find the Taylor series of f at a equals 0 and a equals 1. Okay. Yeah, think about this problem. How to do that? Okay. Right. So let's answer the first question. Taylor series for the function at origin. Right. You don't need to do anything. Taylor series at a equals 0. That's it. That's the function itself. Why? Because this is already a polynomial. Finite many terms. Again. Yeah. So that's going to be, first of all, let's write down the definition, right? X to the nth power, and this must be that term. So you don't need to do any computation, it's guaranteed. Okay. How about the Taylor series at a equals 1? I needed to express it. I think this is 1, n factorial x minus 1 to n. I think the highest order will be, you have to find all the coefficients. Okay, x c1, x minus 1, c2, x minus 2 squared, c3, x minus 3 squared, cube. So those are the terms, and no more high orders. You cannot get x cubed, x to 6th power or 7th power, because the function itself is going to be a polynomial degree 5. Okay, so I think there are a couple ways to do it. Either you get the power series representation, okay, to get series, a Taylor series, or you just use a definition, find the derivative many times, 5 times. Okay. So let's do the. I think the definition is a quick way, because how do you find the Taylor series, right? How do you find the power series representation? Right. You have to expand the x plus y. You know, if you need a formula, something like that. Okay. If you remember that formula, we can do this later. Okay. So let's use a definition. So f of x is 4x to the 5th. Then don't make the computation mistakes. It's going to be 6x squared, 20x to the 4th power, right? The second derivative is 12x plus, and 80x cubed, right? Then the third derivative is 12, 240x squared. So it's easy to do computation. 3 times 8, 20. Okay. The fourth derivative is going to be 240 times 2 is 480x. The fifth derivative is going to be 480. And then high order derivative, they're all going to be 0 for n greater than or equal to 6. Okay, now the Taylor series. Okay, it's going to be, the first one is f of 1. F of 1 is going to be 1 plus 2 plus 7. F of 1, f prime of 1 is going to be, 6, when x equals 1, right? 6 plus 20, 26, divided by n factorial, 1 factorial. And the second derivative, here's 12 plus 80, 92, right? And it's 2 factorial x minus 1, 2 squared, okay? And the third one, 240 plus 12, 252, 3 factorial x minus 1 cubed. and then 480 divided by 4 factorial x minus 1 to the fourth power. And here's a 480 divided by 5 factorial x minus 1 to the fifth. So, and let's do a little bit simplification. 52 divided by 92 divided by 2 is going to be 46. Right? So 252 divided by, this should be constant, okay, not fractions. Divided by 6, 42. Right? And 480 divided by 24. It's going to be 20. 20 divided by 5 is going to be 4. Okay. So that is a Taylor series. It is also power series. Convergence you don't need to worry about, right? This is a Taylor series, and clearly this Taylor series is converging to the original function just because it's a polynomial. Okay, there's no it's always convergent. Okay, so it is a power series representation too. It is convergent to the function, right, for any x. Right? Okay, so if you're given power series representation, and if you're given a polynomial, this is already power series representation for the function at the origin. Now, if the degrees are small, then we can solve the problem directly. You don't even find the derivative. Okay, find the Taylor series representation. Taylor series, okay, for the function f of x equals, okay, equals 1 plus 3 square plus 5x cubed at a equals 2, okay? Now, you can use a definition to find it, no problem. What I'm trying to do is apply the same trick. So here's x minus 2 and plus 2. Okay, so this is a u, right? So the function becomes, I'm going to call u, okay, plus 2. So u plus 2 squared and 5u plus 2 cubed. So I'm going to expand it, express it as a function of a polynomial in u. Okay, so 1 plus u plus 2 squared is u squared plus 4u plus 4, right? And here u plus 2 cubed, I remember the formula, u cubed plus 3 times u squared times 2, and plus 3 u times 2 squared, and this 2 cubed. Okay, let's multiply this out. 1 plus 3u squared, okay, and 12u is 12. And here's a 5u cubed plus 30u squared and plus 30u squared and 5 times 3 times 4, 60u. Okay, plus 5 times 8, 40. Okay, so finally, we will get constants, 1 plus 12 plus 40 is going to be 53. And 12 plus 60, 72u. 3 plus 30, 33u squared. Plus 5u cubed. Okay, so that is a polynomial in u. Okay, then you replace u by x minus 2. Okay, and then we solve the problem. So we just re-express a function as a polynomial in x minus 2. And this must be the Taylor series. This must be the power series representation for this polynomial. All right. Now, and yeah, okay, so now we are going to try to recognize a power series as a elementary function. Some power series can be actually, some power series is a power series representation of some elementary functions. Sometimes we can find out such elementary function. For example, think about, right? So if you know this is x to the n factorial, right? This is e to the x. But if I start from 1, this is still power series representation, right? And that is going to be, you're missing one term. So that's why you have to e to the x minus 1. Okay. And if you start from 2, right? So n factorial x to the n is e x minus 1 minus x. Okay. Now, if we are given a power series, that is going to be 1 x to the n over n. Okay. Can we express it as a power series? And so I forgot the formulas, right? So maybe I can. So what is that for? Let's try, okay? So I let, first of all, the radius of convergence is going to be, yeah. So first of all, the radius convergence is 1. Okay, it's easy. It's converging when number 3x is less than 1. So I let f of x to be this function. Okay, so this is for x less than 1, right? When x equals 1, we have trouble. Yeah, this is divergent. Actually, x is not going to be, this series is not going to be convergent when x equals plus or minus 1. All right, so we get this function. It's a pretty nice function, but it's defined in power series. I just said that some function can be expressed by element, the function, some not. But I want to look at, okay, if f of x is going to be that, so what is derivative? So derivative, you just differentiate every term, right? Okay, so now n cancelled out. So you will get x to the n minus 1. So you change the coordinate, changes the index, let the m to be n minus 1. So this is a 1, sorry, 1. So when n starts from 1, m starts from 0. And x to the n. Wow, so I know this is going to be 1 over 1 minus x. Clear? And for x less than 1, right? Okay, so the derivative of the function is going to be 1 of x. Okay. So I'm going to integrate. Right? So the antiderivative is 1 over 1. I say, what is x, right? What is the f, right? So evaluate. I'm sorry for that. So you can, it's just like a solve differential equation. Yeah. So if f prime x equals 1 minus x, right? That's the first condition. Second condition, I know from the above expression, I think f of 0 is going to be 0. So we get an partial or ordinary differential equations, right, with the initial condition, right? Then you integrate on both sides. So the left-hand side, you get an f of x. The right-hand side is going to be, okay, natural log of 1 minus x. I think there's a negative sign on that, and plus constant. That's the identity in general. But since f0 equals 0, so you imply c should be 0. You plug 0 for x into both sides, and 0 is going to be c. So finally, you find out, this is just equal to that function. In other words, and that is going to be that identity. Okay. Then we said we know that, right? Earlier, that's the we actually recover the if we forgot, we cannot memorize all the formulas for the special elementary functions or the power series representation for the special special functions, elementary functions, right? But sometimes we can recover it. Okay. Okay. Given this, okay, my question is, is it convergent? What is the sum if it is convergent? Okay. So, yeah, please work on this problem. What? Where is the music from? Hold on. Let me check. Okay, let's start. Let me discuss this problem. Okay, now I think we don't need to waste time to check whether it's convergent. Okay, and this is clearly, this can be written in the form n factorial, like 3/5 to the nth power. Okay, so immediately I can get e to the 3/5. That's it. It's not only convergent, it's converging to this number, right? Okay. Another here's another problem. Take a look at 1 minus natural log 2 plus natural log 2 square over 2 factorial minus natural log 2 cube over 3 factorial, and keep it going. Okay. Now this series can be written in the form n equals 0, -1 to the nth power, natural log 2 to the nth, and here n factorial. Okay. So again, this is going to be in the form negative of n factorial. So this is the series, power series for the exponential function, right? So that's why it states e to the negative, right? X here is negative natural log 2. So finally, this is going to be 1 over 2. Okay. Right, so last, I want to look at this problem. Have a f of x. Right, it's going to be defined, and this is problem 84, I think. This is defined by this. Here's if x is not going to be 0, 0 if x is 0. Now, this function, at least it's continuous. Okay, let's find the power series representation. Okay, at a equals 0. Now, notice that the limit as x approaches 0, e to the -1 of x squared. And that is going to be e to the negative infinity. So, right, so this clearly is going to be 0. So the function is continuous. Now, whether the function is differentiable, it's really tough to figure out. Okay, but use a power series, yeah, you can find the derivative, second derivative, third derivative. Okay, what, right? Yeah, you can find the derivatives. So does the derivative is going to be 0 now? Equals 0 now? Okay. So what we're trying to do is we're trying to find all the derivatives. Okay. let's take a look at the second derivative. Okay, the first derivative, the derivative at a 0. I have nowhere to go. Just you have to use a definition to find the derivative. Okay, so that is going to be h approaches 0, and here e to the negative 1 over h squared and h. Okay. So you can use L'Hopital's rule. Okay. You can use the L'Hopital's rule to find the derivative. And this is the same as x approaches infinity, e to the negative x squared, and just 1 over x. Yeah, you let h to be 1 over x, change this. Okay, then you get e x squared here as x. I think when you differentiate the numerator and denominator, it clearly is going to be 0. So, the first derivative is also 0. Then you keep it going, and you find the second derivative, the third derivative. I don't have a time, okay? But it's hard, yeah, I just tell you the fact. The nth derivative of this function is always equal to 0 for any n. Okay, for any n. So that means that the Taylor series is going to be 0. Okay, this is going to be identically equal to 0. Okay. So if this claim is true, then I claim that this function is not going to be, does not have a power series representation. Any interval, non-trivial interval, okay, does not have power series representation. Any interval, okay, absolute x is less than r, and here's r is positive, okay? So you cannot find, if you find one, the coefficients must be or 0, then, but the function itself is not 0, Okay, that's an interesting example, clear? Right? If it has, then the power series representation must be Taylor series. But Taylor series right now is all 0. So a non-zero function equal to 0. That's ridiculous. Okay. So we stop here, and let me stop here. Okay.